Equilibrium 3, Le Chatelier's principle. The essential idea: many reactions are reversible. These reactions will reach a state of equilibrium when the rates of the forward and reverse reaction are equal. The position of equilibrium can be controlled by changing the conditions. Nature of science: employing quantitative reasoning. Experimentally determined rate expressions for forward and backward reactions can be deduced directly from the stoichiometric equations and Le Chatelier's principle. Theory of knowledge. The career of Fritz Haber coincided with the political upheavals of two world wars. He supervised the release of chlorine on the battlefield of World War I and worked on the production of explosives. You should think about: how does the social context of scientific work affect the methods and finding of science? And also, should scientists be held morally responsible for the applications of their discoveries? That is a demonstration that you will see in class. Okay, Le Chatelier's principle. What happens if an equilibrium system is disrupted? Well, Le Chatelier said this: that if an equilibrium system is subjected to a stress, then the equilibrium responds in a way that reduces the effect of the stress and establishes a new equilibrium state. So when thinking about this, think about what is the stress, think about how it responds in a way that reduces the effect of the stress, and what will be the new equilibrium. Changing concentration. We've got hydrogen iodide in equilibrium with hydrogen gas and iodine gas. What would happen if the concentration of hydrogen is increased by adding more hydrogen? Well, the stress is the increased hydrogen. The response would be to use up the added H2 to reduce the stress. And how would this happen? Well, the equilibrium would have to shift to the left. Reversing the reaction, we're going to reduce the amount of this, so it would shift this way. You can see here on the graph, you've got equilibrium with the concentration of hydrogen here. Then you suddenly add more, and the equilibrium shifts. So we'll get more hydrogen iodide formed. You can see that would increase. And if it's shifting this way, you're going to get a decrease in iodine and the hydrogen. And you can see that the hydrogen is decreasing and the concentration of iodine is decreasing until a new equilibrium is formed. And do note that the shift in equilibrium reduces the effect of the stress, but it doesn't completely reverse it. You can see there's a higher concentration of hydrogen at the end, so it hasn't gone back to the initial concentration of hydrogen. So, if the stress is to increase the concentration of a reactant, the response to the stress would be to use up the reactant, and the equilibrium would actually shift to the right, shift towards the products. If the stress is to decrease the concentration of the reactant, then the response would be to make more reactant, and so the equilibrium would shift left towards the reactants. If the stress is to increase the concentration of product, then the response would be to use up the added product, and so the equilibrium would shift away from the product, so it would shift left. And if the stress is to decrease the concentration of product, then the response to reduce that stress would be to make more product, so the equilibrium would shift right. Let's look at example 2 here. We've got ethanoic acid dissociating. What will happen to the equilibrium if HCl is added? Well, the stress would be an increased concentration of hydrogen ions. The response would be to use up the added hydrogen ions, so the equilibrium would shift left. A reverse reaction would be favoured. So let's say we've got an equilibrium initially here. What would happen if you suddenly add more H+, it goes up, then it would be used up, but you still end up with slightly more hydrogen ions concentration, and so more ethanoic acid would be formed, and obviously the ion would be used up, and that would lower in concentration. Example 3, sulfur trioxide making sulfur dioxide and oxygen. What would happen if the volume of the reaction vessel is decreased? So if you decrease the size of the volume this takes place in, imagine it was in a plunger and you push the plunger. Remember Boyle's law, pressure is inversely proportional to volume. So a change in volume will cause the pressure of the system to change. The stress will be decreased volume or increased pressure. The response would be to reduce the pressure. And how would this happen? To reduce the pressure, you'd reduce the molecules of gas. So you'd shift to the left. There's fewer moles of gas. You see you've got 3 moles of gas here and 2 moles of gas here. Increase the pressure, it's going to shift this way to decrease the molecules of gas. So you've got equilibrium here between the sulfur trioxide, oxygen, and sulfur dioxide. At the 16-minute mark, you add, you decrease the volume, increase the pressure, and so it's shifting to the left. So the sulfur trioxide will increase, the sulfur dioxide and oxygen will decrease, and then a new equilibrium is formed around about the 24-minute mark. So if the stress is to increase volume or decrease pressure, the response would be to make more gas particles to increase the pressure. The equilibrium would shift to the side with the more moles of gas. If the stress is to decrease volume or increase pressure, you'd make fewer gas particles to decrease the pressure. And the equilibrium would shift to the side with fewer moles of gas. Example 4, we've got nitrogen and hydrogen forming ammonia in this equilibrium. What would happen to the equilibrium if the volume of the reaction vessel increased? Well, you decrease the pressure, and so you'd want to increase pressure by making more gas molecules. And how do you do this? You'd shift the equilibrium to the left this way, because you've got 4 molecules over here, and you've got 2 over here, so the reverse reaction would be favoured. So you've got this equilibrium set up on the graph. You increase the volume, decrease the pressure, and so the reaction will push this away. You decrease the concentration of ammonia and increase the concentration of these two. You get a new equilibrium. Example 5, nitrogen dioxide going to N2O4. I'm going to change the temperature here. It's exothermic, that way. Endothermic would be the reverse reaction. If we would increase the temperature, the response would be to use up the heat. Try and decrease that temperature. So it would favour the endothermic reaction. So the reaction would shift to the left, you get more nitrogen dioxide. So we've got nitrogen dioxide and N2O4, exothermic to the right. If you were to decrease the temperature, the response would be to release energy to combat that decrease of temperature. We favour the exothermic reaction. The reaction will shift to the right. Let's have a look at this table. If the stress is to increase temperature, the response is to use up the heat, and it favours an endothermic reaction. If you decrease the temperature, the response is to release heat, and that would favour an exothermic reaction. Example 6, you've got the evaporation, the boiling of water, sorry. What happens to the equilibrium if the temperature of the reaction vessel is decreased? Well, the temperature is decreasing, so the response would be to produce heat. The equilibrium is going to shift to the left, favouring the exothermic reaction. So you've got that steam is going to decrease. You're going to have less steam over time if you decrease the temperature, which makes sense. carbon monoxide and nitrogen monoxide. What would happen if a catalyst is added? Well, a catalyst increases the rate of both the forward and reverse reactions equally, and so there's no shift in equilibrium. The equilibrium will be reached sooner though. What are the effects of the equilibrium, or effects on equilibrium constant values? Let's have a look at this reaction with carbon and water, making carbon monoxide and hydrogen. You can see these initial concentrations in blue there. I've done the math for you. The rate, the equilibrium constant value would be 0.036 for that. What would happen if we increased the concentration of water? Nothing. If we increase the concentration of hydrogen, there's no change. Decrease the volume, still the same. However, if you increase the temperature, you can see that that rate, the equilibrium constant has increased. So you've got more products. If you decrease the temperature, that equilibrium constant has gone down. So no effects by changing concentration, no effect by decreasing volume, but you do increasing temperature increases the equilibrium constant, and decreasing temperature decreases it. So the effects on equilibrium constant values, the Kc values will only be affected by a factor that affects the rate constants of the reverse and forward reactions differently. So concentration is the same both ways, as is pressure, as is a catalyst, but temperature will change. So, and it'll depend on the sign of the enthalpy change and the change in temperature. Example 8, we've got nitrogen dioxide giving us N2O4 again. You see it's exothermic reaction. What will happen to the value of the equilibrium constant when the temperature decreases? The exothermic reaction will be favoured when temperature decreases. So more products will be formed, you get less reactants. You can see here that the K forward increases, so we get more products, and therefore the equilibrium constant will increase. I would like you to do now is to fill in that last table from the notes you've already made. And that's the end of this presentation. Splendid.